The Engineering of Large Software Systems, Week 8, Strategies for Efficiency and Effectiveness. This week, we will survey a number of strategic approaches to more easily develop large software systems. These are big ideas, but require vision, courage, intention, perseverance, and detailed execution to deliver the promised benefits. None are silver bullets. None apply to every large system. Knowing about them can help define the processes and life cycle appropriate to your system at hand. We'll look at operational concepts, enterprise architectures, governance models, reuse, COTS, open source, product lines, patterns, and model-based development. Operational concepts, concepts of operation, or CONOPS, are most often associated with systems engineering. They are the repository of the system's user-facing components, and so provide a means of evolving a common vision among stakeholders, or at least recording the existing differences in the resolutions agreed to. Both the as-is and to-be mission environments are captured. But within an operational concept, the system under development is a bounded black box. Operational concepts do not need to be prose documents or flow diagrams. Depending on the changes expected, they may include models, prototypes, and/or recorded discussions and presentations. In large systems with many and varying stakeholders, a good operational concept will support systems requirements identification and can stabilize and manage the system in the face of environmental changes. The concept of an enterprise architecture is well known in the information technology world. For our purposes, however, we will be using the broader systems engineering definition to include the system and its environment, as well as the enterprises responsible for developing and operating it. Of course, the enterprise architecture must be aligned and consistent with the operational concept. Governance is the way in which organizations make decisions. Governance cannot be left to chance in large systems. Explicit chains of responsibility, authority, and communications need to be in place and understood. Included in these chains are the success-critical stakeholders. Governance doesn't mean that the organization must implement top-down command and control authority. A governance system can give responsibility and authority wherever it is needed. It just does this intentionally and doesn't leave critical decisions to chance. The governance system is the way that operational concepts and enterprise architectures can evolve in a controlled and consistent manner. Reuse is a highly effective way to increase the productivity and efficiency of software or systems organizations. Reuse implies developing systems using pre-existing software development assets. This doesn't mean just software is reused. Designs, patterns, models, schemas, architectures, in fact, anything previously used to develop software is a candidate for reuse, and we'll talk about several special cases of this. While seemingly obvious and pretty simple, reuse is often planned for, but not successful. It requires careful strategies and ruthless conformance to positively impact projects. Too often, the amount of reuse is underestimated. This can be due to unexpected complexity or undocumented actions in existing assets, unforeseen interactions between components, or changes in the initial assumptions of the asset reused. The Ariane 5 failure is a good example of changes to initial assumptions. The Ariane 5 rocket software reused the specifications from the Ariane 4 rocket, but the Ariane 5's flight path was considerably different and beyond the range for which the reused computer program had been designed. Pre-flight tests had never been performed on the reused software under simulated Ariane 5 flight conditions, so the error was not discovered before launch. Reuse is often used to make significant reductions in the projected cost of systems. Unfortunately, calculating the real benefit of reuse is also a problem. The counting methods can vary significantly and can change the way in which value and risk are determined. Suppose there are 10 software modules, each with 1,000 source lines of code. A project modifies 300 source lines in each of 4 modules and leaves the remaining 6 modules untouched. Okay, if we just look at the number of lines of code, only 1,200 lines of code changed out of 10,000, which gives us about an 88% reuse. Wow! Managers and executives are cheering. We're saving lots of money. However, suppose that we look only at the modules. In that case, 4 modules change out of 10, only 60% reuse. The managers and executives and accountants are somewhat less excited. More importantly, the predicted schedule and cost savings also change. Because of the amount of extra analysis and testing associated with changing code in any module, modifying 100 or so software lines of code in one module does not have the same risk and benefit as modifying 10 source lines of code in each of the 10 modules. This graph illustrates the difference in predictions and reality that NASA discovered. Commercial off-the-shelf systems are a very special kind of reuse that at one time was considered a silver bullet in many acquisition organizations. It can be robust and have nearly immediate value. You get working code that provides specified functionality, and someone else maintains and evolves the product. The cost of the product is amortized over many sales, and there is motivation on the vendor's part to make the software reliable. Now for the downside. You get what you get. You usually can't easily modify the functionality, which is often defined to meet a more general consumer need. The functions available in the COTS will drive the requirements as much as the user needs. This means that your stakeholders must be willing to compromise. You have limited or no visibility into what is actually happening in the COTS. And that can be frustrating and dangerous. Remember that invisibility werewolf. You probably have very little say in the evolution of the product. New releases generally come out every 12 to 18 months. These changes must be accommodated by the parts of the system that rely on the COTS, leading to long hours of analysis and testing. If the vendor decides to move into another market or architecture, you need to follow, or you have to replace the COTS with something else, and that's a very expensive proposition. The most significant problem with reuse, whether internal or external, is evaluating how existing software functions in a new environment. Certainly, software developed for a business system may be completely inappropriate for a safety-critical system, even if the functionality is exactly what you want. Of course, the Ariane incident shows that even similar environments can make reuse difficult. Another example of this is when the U.S. sold some air traffic control software to Great Britain, which provided some surprising results. Since the U.S. coordinates have only west longitude values, there had been no provision for east longitude. So, in essence, the airspace of Great Britain was folded in half at the Greenwich meridian. If this had not been discovered in testing, there would have been some really interesting flights over London. These issues are becoming more and more common as the number of truly clean sheet of paper or greenfield systems drops and the percentage of brownfield systems that are based on reused legacy software or COTS increases. Open source software is one way that developers are trying to merge the benefit of COTS with the visibility of custom-designed code. Open source is developed in a collegial environment where the actual code is provided to anyone who wishes to modify it. Generally, there's a small group that arbitrates when changes become part of the official open source product, but that may be of little interest if the code modifications are not intended for the general public. The largest open source projects, such as Linux, Apache, and Eclipse, have thousands of contributors, but most of the open source projects have a small, dedicated, and often feisty core of developers. Open source provides rapid evolution, quick repair of bugs, and because it is open or white box, you can't hide flaws or malicious code, something security experts are still debating. Licenses for commercial use of open source products vary widely, and the lawyer's fees can sometimes eat up any projected savings. A software product line is a set of software-intensive systems sharing a common managed set of features that satisfy the specific needs of a particular market segment or mission, and that are developed from a common set of core assets in a prescribed way. The effectiveness and efficiency of product lines comes from very disciplined planning and architecting for reuse. The Software Engineering Institute at Carnegie Mellon has done a great deal of work in product line concepts and implementation guidance. Product lines allow a project or organization to amortize their investment in some core assets. For example, requirements and requirements analysis, domain models, test plans, test cases, and test data, as well as processes, methods, and tools. Product lines provide strategic reuse rather than opportunistic reuse. Implementing a product line is not an easy task, but it can provide significant savings and efficiencies if well conceived and managed. The SEI has developed a web-based framework to help with product line implementation, and there is a link to the site in the course material. There are also several product line case studies available in the reading material, or you can follow the Product Line Hall of Fame web link. Architectural and design patterns are also a form of reuse. They grew out of work by a number of object-oriented developers, including Kent Beck and Ward Cunningham of extreme programming fame. They were first studied academically in Eric Gamma's doctoral dissertation and gained broader awareness from the Design Patterns book by Gamma, Helm, Johnson, and Vlissides, also known as the Gang of Four. Patterns document commonly used approaches to specific problems in such a generic way as to be easily applied in other instances. Patterns can be considered both knowledge artifacts and reuse components. Model-based development is an approach that uses models to bridge the conceptual gap between domain experts and product developers to eliminate rework and deliver acceptable products sooner. It is essentially synonymous with model-based architecture. There are several varieties that use models in different ways. Some use a standard modeling language like UML or SysML. Others use more simulation-based model descriptions. The goal, which has not yet been achieved, is to have the user describe a problem in a modeling language that applies in the user domain, and by translating the model into more and more detailed models, the end result is executable software that traces directly back through the models to the user's description. We've looked at a few of the strategic approaches that can be used to improve the effectiveness and efficiency of large software developments. We'll see others that may apply at the tactical level later in the course.